All right, so we are going to look at forces that we encounter, common forces here on Earth, and sort of compile a list of them, of the forces you might encounter. So the first force is probably the most familiar to you, and it is the force that we measure when we stand on a bathroom scale. So gravity pulls all objects towards the center of the Earth, and this pull of gravity is a force. And when we measure that force, we are measuring our weight. So weight is the name we give to the gravitational force that is pulling us towards the center of the Earth. So that's weight. All right? So really, when you find your weight, what you are measuring is the force of gravity pulling down on you. So if you weigh 150 pounds, that means gravity pulls down on your body with 150 pounds of force. If you go to college and eat too much your freshman year and maybe you gain 10 pounds, what that means is there's now more of you. And so the force of gravity is, of course, larger pulling on you because there's more of you to pull on. And so you might be 160 pounds or something. Okay, so anytime you hear the word weight, think force of gravity. All right, that's the name of the force. Now, it turns out, like we saw in class, that whether we drop a tennis ball or a croquet ball, which is much heavier, or a golf ball or a bowling ball or anything, even the foam ball, they all accelerated downwards at the same rate. Okay? And this is somewhat confusing at first. You wonder, why does a heavy ball fall the same rate as a light ball? Well, it turns out that the force of gravity pulling on an object depends on its mass. So according to Newton's law, the net force acting on an object equals the mass times the acceleration. So if you have a bigger mass, then you have a bigger force. But you also have more inertia. And so the rate that they fall is always the same. Okay? So if gravity is the only force acting on an object, it's going to accelerate downwards at 9.81. So we can calculate the force of gravity. The force of gravity must equal the mass times the rate that it's accelerating. And this rate is 9.81. So since we know the acceleration due to gravity is 9.81 meters per second squared, and we call that g, then the force that gravity must exert must equal the mass times the acceleration, or m times g. So you should put this in your toolbox. This is how you calculate the weight of an object, the force of gravity pulling down on an object. Anytime you want to find the force of gravity pulling on an object, you take the mass of the object in kilograms, multiply it by g, which is 9.81, and you'll have the force of gravity, or the weight. Okay? That's how hard gravity pulls down on an object. Pause the video if you need to and write that down in your toolbox. Okay? So we got the big idea that the net force causes the mass to accelerate, and now we're adding this little idea that the force of gravity is always equal to m times g, or at least on Earth it is. Okay? So if you have a person who weighs if they have a mass of 60 kilograms, what is their weight? So when we say what is their weight, we're asking you to find the force of gravity. So remember, the force of gravity is m times g. You just take the mass, 60 kilograms, multiply it by the acceleration due to gravity, which is 9.81, and you will have the weight every time. So in this case, a person whose mass is 60 kilograms has a weight of 590 newtons. That means gravity pulls down on them with 590 newtons of force. All right? And this, of course, goes downwards. So we just remember, this tells us the size of the force, but gravity always pulls us downwards. That's how we define down, actually. It's the direction gravity pulls us. Okay, so if you know the mass of anything on Earth, you can find its weight. You just take m times g. All right, that's the first force we're going to look at. Gravity is the weight. Now, if I had a book and it's sitting on a table, gravity pulls down on it with a force we call the weight. But that book doesn't accelerate downwards because there's another force pushing up on it. The table that it's resting on is pushing up on this book, and we call those forces normal forces. So an upwards force exerted by a solid surface, like a table or the ground or the road or the floor, any of those, if a solid surface is pushing on an object, we call that force a normal force. In mathematics, normal actually means perpendicular. So if this is the surface right here, the table, the force acts perpendicular to it. That's why it's called a normal force. So if you wonder why do you not fall through the ground when you're standing on the floor, it's because the floor pushes up on you, and we would call that a normal force. All right? So that's a normal force. And these normal forces always act perpendicular to the surface. Another common force is a tension force. So if you have something like a chandelier or something and it's hanging here, of course gravity pulls down on it, so there's a force going down. And if there was no cable here, the lamp would fall. But it doesn't. There's a force pulling up on it. Now, a lamp that is, or a box, let's say, that's hanging from a rope, it's not resting on a solid surface, so there's no normal force on it, but there is a tension force. So tension forces are the forces that are exerted by flexible medium, like a string, a cable, a wire, those kinds of things. So anytime you have a wire or a cable or a string or a chain pulling on something, we call that a tension force. Okay, so a box hanging from a rope would have two forces on it. There's always gravity acting down if it's on Earth, and there's a force pulling up, and that will be the tension force. Another force is friction forces. So friction forces act when objects are in contact with one another, and they're always in opposite directions. So if I had a box on the floor, and the box was sliding to the right, then friction would act to the left. If the box was sliding to the left, friction would act to the right. So friction always opposes motion, and it happens when two surfaces are in contact with each other. So if you actually look at this box right here, gravity is pulling down on it. That's the force of gravity, the weight. The floor is pushing up on it. I didn't draw those two forces. Maybe I should have. The block is sliding to the right, and so there's friction to the left if these two surfaces are in contact. All right? So that's friction force. Now, what about your car zooming down the road? What kind of force is acting on it? Well, if it's cutting through the air, there is what we call a drag force. So anytime an object moves through a fluid, there is an oppositional force called a drag force that always opposes motion. So if your car is going north, the air resistance acts towards the south. If your car is going east, the air resistance acts towards the west. If you are in free fall, skydiving, and falling downwards, the air resistance acts upwards. Okay, so it always opposes the motion. So these forces point in the opposite direction of the velocity. And these forces are velocity dependent. If your car stops moving, the air doesn't exert a force on it anymore. Or if you stop moving, there's no drag force at all. Okay, so drag forces are forces that are created because something is in motion in a fluid. These are most common when something's moving through air. We call that air resistance. Or through water. We call that drag or water resistance. Okay. Another force is a buoyant force. So you might have a boat. This is not a solid surface that it's resting on, so it's not a normal force pushing up on it. Clearly, gravity pulls down on it. That's called the weight. But the force going up on it due to a fluid is called a buoyant force. And we'll study that later towards the end of the year. We'll do a unit on fluid physics. But that's a buoyant force. So upwards forces on an object that are immersed in a fluid are called buoyant forces. So if you got a hot air balloon that's rising in the sky, that's because there's a buoyant force on it. Gravity pulls down, the buoyant force goes up, and if the buoyant force is bigger than the gravity force, your hot air balloon will actually go up and up and up. It'll accelerate upwards. Okay, so even if something's resting on the bottom of the water, there's still a buoyant force, and there may be a normal force also if it's resting on the ground here. But the buoyant force is the upwards force of an object in a fluid. These aren't generally significant when we're in air. You don't really notice the buoyant force on you because your volume's not very big compared to your weight, okay? But when you're in water, so like boats and submarines and stuff, the buoyant force is really big. And then any force that doesn't fall into one of these categories, we call an applied force. So an applied force is any force, like you push on a wagon, you push on a box, you pull on a dresser as you're moving it. all those things, if they don't really fall into another one, they're kind of, done by somebody pushing or pulling with their hand. We call those applied forces. So here's our summary of forces. These are the ones you should be able to identify. The first one is the weight. We are going to use the symbol F sub g. So F is a force, and the type of force is the subscript. So F of g is the force due to gravity, which is called the weight, and you can calculate it by taking m times g. The first couple problems in our homework assignment coming up will be doing those. A normal force is F sub n. This is the force exerted by solid surfaces like the floor or the table. A tension force is F sub t, and that's the force exerted by strings and ropes and cables. Friction force is F sub F, and we use a little f here. Those are friction forces. That's when two surfaces are in motion relative to each other. So like a box sliding across the floor or something, a hockey puck sliding across the ground. And friction forces oppose motion. An applied force is any force we're not sure of, like a hand pushing on something. That's F sub A. We're going to use F sub B for buoyant forces. So those are forces exerted by fluids. They always point upwards. They always oppose gravity's force. And F sub D is a drag force. That's the force you get when an object is moving through a fluid. It opposes motion. Okay? So if you're moving through a fluid, what opposes motion is the drag force. If you're sliding across a solid surface, what opposes motion is the friction force. All right? So what you're going to do is a little activity where you're going to build some free body diagrams. So let's just do a practice one here. I've got a free body diagram. It's just a way to draw the forces on an object, okay? So when we draw a free body diagram, we're going to draw the forces on the object. We're going to show what direction they're going, how big they are, and what type they are, all right? The object that we're interested in, we always draw as a dot. It's called the free body, okay? And then we're going to draw all the forces as arrows. And we always label our arrows. If you don't label it, it's not a free body diagram. The forces always start on the object and they point away from it. So let's just try an example to kind of put that all together. We have a student and they're going to pull a dresser across the room to the right. So we've got a dresser. That's the thing we're interested in. A student is pulling it to the right. There's friction present and the dresser accelerates to the right. We need to draw a free body diagram showing all the forces. So here we go. There's our dresser. Okay, so we're going to represent the object as just simply an object hanging in space. And we need to draw the forces that are acting on it. Now, if this object is on Earth, you automatically know one of the forces. It is the force of gravity, and it points down. Okay? So that's a freebie. Every single problem that involves something on Earth, it's going to have a force on it pulling down called the force of gravity, or the weight. Okay? Now, this dresser doesn't fall downwards though, because the floor is pushing up on it. And so the force going up on it opposes gravity, so it's the same size, so it's a balanced force, and because it's exerted by a solid surface, which is the floor, we call it a normal force. Now, the student is pulling the dresser to the right, so there's a force going to the right, and since the student is pulling it, he's not using a string or anything. We call that an applied force to the right. And friction is present. And which way does friction go? Well, it says the dresser accelerates to the right, so it must be moving to the right, so friction must act to the left. And now here's one more detail I want you to notice. Not only did I put all the forces and label them, but since the dresser accelerates to the right, there must be an unbalanced force to the right. Because if the forces are balanced, it wouldn't accelerate. So, if there's an unbalanced force to the right, it means this force here has got to be bigger than friction. So you see how I drew my arrows to show that? If an object is accelerating in a certain direction, the forces going in that direction have got to be bigger than the forces going in the other direction. Since the normal force and gravity force are the same size, they are balanced forces. They cancel each other. The dresser doesn't move up or move down. But the forces horizontally are unbalanced. The force to the right is bigger than the force to the left, so it accelerates to the right. So what you're going to do next is work with a simulator, which is going to give you some problems, and you're going to construct free body diagrams. It can get a little frustrating. So watch the tutorial to see how to work the app, and then you're going to build free body diagrams, and when you get all done, it'll give you a completion code that you can turn in. Okay, so that's the next thing to do. All right, good luck with that.